Okay, welcome back. And I'm so happy you have a responsible chair that reminded everyone to come back. We're going to listen to Chen Zhao, who's going to talk about ISMIP6-based projection of Antarctic contribution to sea level rise.
Hello everyone, I'm Chen Zhao from the Australian Antarctic Program Partnership in University of Tasmania. First, I will say thank you to Jordan for the invitation, and very happy to be here for actually the motor. And I have to say, for the first time, I was surrounded by so many sea ice people, but I love it because for the ice sheet we need more opportunity from more things. Yeah, pretty happy to be here. And today I'm going to talk about our recent contribution to the ISMIP6. And this work has been collaborating with my team. They are Thomas Linger from the CSC in Finland, Rupert Gladstone from the University of Lapland, and Yu Wang is my PhD student in UTAS, and Ben Gomitensi from the Australian Antarctic region. And this work is part of our contribution to the ISMIP6. And ISMIP6 is the ice sheet models in the comparison project for the CP6. It has two different phases in 2019. The first phase mainly relative relation to the end of the 2100 years, and recently we have a second phase to extend our simulation to the 2300 years. Okay, let's start from the sea level rise projections. So back to the IPCC-5, we'll know that the sea level projections were mainly based on the extrapolations from the observations and also the expert analysis. And that's because in that time, our physical models were not ready or not good enough to provide us the sea level projections. However, the ice sheet community, ice modeling community, and also the climate model community, they have done tremendous efforts to make it happen. And the latest attempt was made by the ISMIP6 community. And in this table on the left, it shows us the first phase of the ISMIP6. We have more than 13 groups from around the world, the different action modular groups. And as one of them, we UTAS will contribute to this ISMIP6 using the ALMA ice action models. And the table on the right just showed us the climate forcing file we used from the different climate models. So for the first phase of the ISMIP6, we don't have, the CMIP6 actually was not ready for the ISMIP6. So in that phase, we just use the models, climate models from the CMIP5. And luckily, finally, this year, when we start the second phase of the ISMIP6, we have two new models from the CMIP6. I'll explain it later. Okay, so this plot is from our first phase of the ISMIP6, the 2100 simulations. And this is the sea level contributions relative to the control run, and kind of give us a general idea from different scenarios under different climate models under the high emission scenarios. And the thick line here is the mean average sea level contribution for each climate models. And the range here around these thick lines were provided by different action models. And we can see that the range is pretty large. We can range from a minus 70.6 to 30 centimeters. And the purple line here from the head jump 2 model gives us the largest ice mass loss from Antarctica. But while the yellow line here from the CCS-M4, this model just shows us Antarctica was thinning ice rather than losing ice. So we can see that we still have very large uncertainties in the projection from the Antarctic contribution. And here is another plot. Just give us some general idea about the regional changes in the sea level projections. And from this map, you can see that for the West Antarctica, most of the simulations just show us that West Antarctica was losing ice. But if we look at the East Antarctica, many models just give us the idea that East Antarctica was gaining ice. Is that true? But that's the model give us. I was quite interested, how it's going to be for our new simulation to run in order to the end of 2300 years. That's something I'm going to show you later. So keep this picture in mind, and we'll go back to this picture later. Okay, this picture is pretty familiar from Blazing Talk, and please show this map. Just give us a general idea about the past. So we got this kind of mass loss from the period from 2003 to 2019 using the observation from ISMIP6, and we can see that there are two regions, very area here is the Amazon Sea region here, and also the Wilkes Land in the East Antarctica. They gave us the rapid ice mass loss in the past. Actually, in our 2100 simulation, we also found that those two regions are the most vulnerable regions, which is very similar to the changes in different simulations. So it's pretty consistent to what we observed in the past. Okay, so as I mentioned that in our ISMIP6, we used the scenarios from the previous generation, ISMIP5, but we really want to know like how the sea level will going to rise under the new, new shared social economic pathways. So our team just combined our projections from both Antarctic and Greenland to use innovations for the different action and the climate models. It just provide a land ice contribution to the sea level rise. So this is the plot we saw here. So if you look at the mid projection here, you can see that under very if we can limit the global warming to 1.5 degree warming, that's this green point here. We can just get the sea level contribution half if we compare to the current emission plan. And in this simulation, the scientists found that Antarctica is not similar to different scenarios. It gives us nearly same numbers from Antarctica. But if we take everything, to be very pessimistic, and in that scenario, Antarctica can behave very crazily. So in this projection here, Antarctica can be have 4 times higher contributions compared to with these mid projections. So this is another solid evidence to show us we still have large uncertainties in our model projections. But the good thing is that finally, for the first time, the latest IPCC report finally got the results from the ice sheet modeling community, and also combine the results from different ice sheet modeling communities and provide this plot here. And as part of the ISMIP6, we should provide the medium confidence projection in this plot here. So based on this map, we can see that under the very high emission scenario, the sea level will rise around 63 centimeters to 100 centimeters. But I want to emphasize the dashed line here. So the dashed line here told us that the possibility of around 2 meters sea level rise before the end of this century could not be ruled out, just because there are so many uncertainties in the actual processes represented in our actual models. Okay, back to our latest ISMIP6-2300 projections. As our group, we just contributed highlighted experiments using 3 different ISMIP5 models and 2 different ISMIP6 models. As our contribution, we use the ISMIP action model. ISMIP is a finite element action model. In the 2100 simulations, we adopt a full slopes action models, but with a very poor resolution, is about 4 kilometers near the ground line. So the ground line is a black line here is where the ground ice become float. It's very important feature in the action models. And we for the basal sliding, Felix just mentioned, and we adopt very simple sliding law, linear sliding law. But for the basal melt parameterizations, we just adopt the standard ISMIP6 approach, just as I showed in this equation here. And the only parameters here is vary with time in the thermal forcing from different climate models. In our recent contribution to the 2300 year simulations, due to the time and to achieve the deadline, we have to adopt simpler Eskimo equations. So we use the shallow shelf of approximation, which is much more cheaper than the full scope, but it allows us to use a higher resolution. So this time we just adopt 1 kilometer near the ground line, just like the mesh here showed us. So the mesh here is zoomed into the Thai Island and the twists, and we can see that the pretty high resolution near the ground line. So other configuration totally same with the previous simulations. Okay, so to get the initial state, we use the model to calculate the mismatch between the observed and the simulated surface velocity, and we got the basal drag like this map shown here on the base, and also we got the ice viscosities. And by combining those two different data sets, and we assume the initial geometry to be the start of the simulation and run it to the end of the 2300 years. And these two plots here just give us a general idea about the forces we use to constrain our model. And one on the left is the Antarctic surface mass balance anomaly. And you can see that the orange line here from the ISMIP6-based, they gave us the largest mass loss on the surface. And then it's the purple line from the UKESM. And then it's the yellow line, the ISMIP6. So I want to mention that those two models are all from ISMIP6. Let's look at the base. So this is surface, and then this is base. So the base of that shelf, we just generated this basal melting flux from our model outputs, and you can see that in the first 100 years, we didn't see much difference for most models, but after 2100, you can see that the purple line from the UKESM and the yellow line from the ISMIP6 gave us very large mass loss at the base of that shelf. So keep that in mind. And this plot just is from our models, just using the LMAS models to give us a general idea about the sea level contributions. So the green line here is using the model with a very low emissions, and the other lines all represent the model outputs from the high emissions. So from our model output, we can see that the Antarctica is always losing ice, no matter if it's a low emission scenario or high emission scenario. But the range is still large. It's from 33 centimeters to about 2 meters. And here I want to mention that the dashed line is using the climate models with a repeated forcing after 2100 as a comparison with the models with a continued forcing. And by comparison, the same color, but with different dashed line and solid line, we found that those experiments with the repeated forcing always give us much lower estimate loss in the model. And another thing I want to mention that you can see the purple line and the orange line give us the top two mass loss in those models. And I want to mention that they are all from the ISMIP6. But unfortunately, I don't know too much about the performance between the ISMIP5 and the ISMIP6. Hopefully, in the coming AGU meeting, I think that ISMIP6 community they will give a talk about all these different results from different action models. I hope they will give us a general idea about the different performance between those ISMIP5 and ISMIP6 models. And if we just look at the first 100 years from our result and compared with the ISMIP6 200 years result, and we can see that the model gives us the most mass loss from our model is still same with the ISMIP6 2100 projections. Although color is different, but I want to mention that that's from the same model. The yellow line here is the ISMIP2, and this purple line is ISMIP2. But after 2100 years to the end of 2300 years, we got pretty much mass loss from the ISMIP6 models. So I want to show you something fancy from the animations, and we'll just take the extreme case from the purple line here. So the purple line is the result give us the largest SMS loss. I just want to give you some general idea about how the Antarctic is going to change in our extreme case, which could be true because we don't know everything could happen. And for this animation, it's showing us the asynchronous change rate across the whole Antarctica. And the blue means is thinning, and red means is thickening, and the a black line here showing us the ground position. And please pay attention to the ground position. Okay, let's play it. You can see that in the first 100 years, a lot of things happening for the West Antarctica, and after the second 100 years, something happening for the Totten and also the Wilkes subglacial basin here. And end of the third 100 years, something really happening for the Denman-Shackleton region. This is the very terrifying thing, especially when we look at the last year of the simulations. You can see that the ground line of those three different ice shelves is very close to each other, and can be very scary thing to see them connect each other. So if we go to the next one, I want to also show you the simulated surface velocity from the same experiment. So in the first year, you can see the rapid ice mass loss mainly focused on the twists in the West Antarctica, and then we see the Cook start to accelerate a lot, also for the Ross ice shelf. And all of a sudden, we see something happening for the Denman-Shackleton region, because we all know that in the Denman glacier, actually, we have the deepest ice shelf beneath the ground part. So once the ground line retreat back to the big trough, we can have very, very rapid ground retreat. It's going to happen just in a few years, and can give us very, very rapid ground line retreat, and also the ice mass loss. So for our Australian community, we are more interested in the East Antarctica. So let's look in this plot to see what's going to happen for the East Antarctica. So this is Denman, Totten, and here is Cook, Ninnis, and Mertz. You can see in the first 100 years, nothing really happening except for Totten. And then I want you to pay attention to the ground line between the Totten and its neighbors. See, they just connect each other. And also similar things happened for the Cook, Ninnis, and the Mertz. And we realized that once their ground line connect each other, it can just lead us more rapid ground line retreat, because we have more warming ocean water just comes through the channels beneath those new floating areas. So that can be very terrifying thing for us to see in the future. And also, I try to calculate the sea level contribution from those three different catchments, mainly based on the catchment here. So I just adopt the pink and blue area for the Wilkes and the Aurora subglacial basins and plot it here. We can see that Aurora subglacial basin is always the largest ice mass loss contribution in the East Antarctica, and that is the Denman-Shackleton region, and that is the Wilkes subglacial basin. But the sad thing is that in the East Antarctica, we still have quite large data gap. So we don't have so many observations in the East Antarctica. So in our models, we lack a lot of constraints in our models. So a lot of large uncertainty from those kind of large data gaps. Then what's the future of the East Antarctica? That's some question I think most of the people here are very interested in. And for me personally, I'm very interested to know which glacier in the East Antarctica is the first one to reach the tipping points actually, and which glacier is going to reach that point and have huge changes. That's the kind of question I'm very interested in, and that's the question we can use our models to answer actually. Here's another plot I made based on our model outputs. It just gives us regional changes for those different time periods. For the first one here is just across the whole 300 years simulation. You can see that most of the simulations from different climate models give us idea like the East Antarctica was contributing more than West Antarctica across the whole 300 years. But if we look at the three different 100 years, and actually for the first 100 years, in the ISMIP6 100 years projection, the ISMIP6 coming to give us a conclusion saying that the West Antarctica contributing more than the East Antarctica. But in our model simulations, we are quite sensitive to the choice of different climate models. So yeah, for this point, we are not so confident to say that like our result is more accurate, because it's hard to say. And for the second and the third 100 years, you can see that East Antarctica plays more significant role compared with West Antarctica, and we can see a very large mass loss compared with the West. Okay, of course, all my talk I mentioned a lot of times about large uncertainties. So finally, I want to just give a summarize about the three different sets of uncertainty exist in our sea level projections. The first one actually is the largest gap actually in our projections, is more about the physical understanding and the implementations of the key physical processes in our action models that include like the ice shelf ocean interactions between the ice and the ocean, boundary layers, and also the subglacial hydrology beneath the ground ice, how it will influence the basal flooding of the ground ice, and how the meltwater from the subglacial hydrology will influence the ocean circulation beneath the ice shelf canopy. This is another very interesting question we need to answer in our action models. And the last thing is very popular term recently. It's called rapid ice cliff collapse. Actually, in most of our ISMIP6, actually all of the ISMIP6 simulations, we don't have this rapid ice cliff collapse instability included. So that's why we see those dashed lines give us the extreme case of 2 meters sea level rise by the end of this century. In that simulation, actually, they consider the influence of this MICS, the ice cliff impact. And the sixth thing I want to mention that we have so many different action models. We have so many different like initial conditions and boundary conditions. So that's a difference from the different glacier models. And also lastly, the different climate models. We hopefully in the future we can have like more high resolution climate model without constraining our action models. So that's one thing we can make more efforts. Okay, lastly, I want to share my future interest mainly from this plot. And so personally, I'm more interested in the two different physical processes offered in the ice shelf cavity. One is about the ice-ocean interaction here happened between the ice and also ocean, and also for the impact of the subglacial hydrology on the basal flooding and also the ocean circulation, and further to reduce our uncertainties in the ice shelf in the sea level rise projections. Okay, so that's pretty much the main points I want to deliver through my talks. I also want to mention that the ISMIP6 committee, they're going to give a talk in the coming 8 years. Hopefully they will just show us more information about the different models and different results, and especially about the performance between ISMIP5 and ISMIP6. Okay, yeah, that's pretty everything. And I want to say thank you and sorry about I can't join everyone for the fancy dinner tonight because after this talk I have to head to the airport to Egypt to attend the call. Yeah.
Thank you very much. Ken, before your flight, we'll see if there are any questions.
Thanks, Chen. That was really excellent. I have two questions. One is, with the grounding line mesh resolution, do you take into account where the grounding line migrates to in setting the mesh resolution, or is that just set based on present day velocities? And if so, what's the impact of that? And then, yeah, maybe, and then I'll ask a second question if there's time.
So that's very good process. Actually, a mesh is generated based on the observed surface velocity. So it's really first on the initial ground level. So that's right. When the ground retreat, like the extreme case I showed for that one, we actually lost a lot of confidence for the new ground level condition because we have very quite coarse resolution for that. So in the future, actually, it's doable. As I heard from Thomas, saying that it can get mesh change with the ground level condition change. Yeah, it's doable.
Yeah. Cool, thank you. The other one was Saipal Coast seemed to be very, very active, and particularly even in the 21 simulations to 2100, and there are some of the ice streams in that region that have been stagnating over recent decades, which is partially what's been explaining the growth in the surface elevation that you see in ISAT. And I'm just wondering if you have any comments on what's happening in the Saipan Coast region that's draining into the Ross Ice Shelf.
You mean the map in the as natural ice section?
Yeah, there's been stagnation of the ice streams in Saipan Coast that drain into Ross Ice Shelf, which is partially why we're seeing surface elevation gain. But in your simulations of future grounding line retreat, that's one of the most active areas for grounding line retreat. And I was wondering if you had thoughts on what are the dynamics in that region.
Absolutely not, because this result just come out 1 month ago, and all these plots are generated last week. So I haven't got time to have a big analysis of the results. Actually, I want to mention that in last week I found something was not wrong. Actually, because I mentioned that I took the initial geometry as the start of the simulation. Actually, we should conduct a historical run to get the geometry to adjust it with the mass and also the velocity, and that kind of underestimate our project estimate. But I will let you know when we get more details from that. Thank you.
Thank you very much. Any other questions? Oh, Siobhan? Anyone online want to ask questions?
Yes, very good talk. That was really interesting. Just one comment about the difference between the CMIP5 and CMIP6 scenarios, particularly out to 2300. In the RCPs, there wasn't really a very detailed emissions in the scenarios. But in the SSPs, they did have more detailed emissions. So it's not really surprising that there was higher responses in your when you use the CMIP6. So the runs would have been warmer, and so certainly that was what I would have expected from your responses. So when you did the UK ESM with SSP, you would have got a bigger response than say when you did the earlier with the Hadley model. So that's really not a surprising. So that's what you would see with all the other responses when you do a comparison with the earlier similar responses. So that should be something that should have been picked up from the climate community.
Thank you for that information. Actually, I did read some papers to compare the same climate models from CMIP5 and CMIP6. Actually, the models using the CMIP6 did provide a better performance. But here, the models from CMIP5 and CMIP6 are different climate models. It's not like the same model from CMIP5 and CMIP6. But it's good to know that updates. Thanks.
They're different models, but there's also different scenarios in the SSPs versus the RCPs. Yeah. There's different emissions in as well. So there's more complexity as well.
Yeah. Okay. Thank you.
Other questions? Well, let's thank Chen again. Thank you very much.